Hello, good morning to everybody here. Nice to meet you. My name is Lukas Malfatti from Röchling Automotive, Global Product Manager for our product line battery solutions. And today in this talk, I would like not to go into detail in software, not into detail in simulations, but I'm working there in a tier one company. We are doing plastics, we are different components. I would like to touch a little bit more hardware potentials that we have in next generation of power electronics devices. And first of all, I would like to give you a glance in who is Röchling Automotive. For colleagues here that don't know us, then a really short introduction of metal to plastic bonding. Maybe this is a technology somebody knows, but not that in detail. And then I would like very quickly to come to our solution study for a DC-DC converter, where we firstly applied on power electronics devices this technology, and sum up with our next vision that we have when it comes to ePowertrain, so power module cooling, and which are related potentials in optimization. Röchling Automotive, 100 years of plastics, 200 years of material expertise. We are a plastic manufacturing company, Germany-based, family-owned, as a group working in 3 different divisions, automotive, industrial, and medical, and roughly with this company size you see on the slide. We from the automotive are, like you can see here on the right-hand side, roughly half size of the group. And we have a very clear vision towards all of our products. We drive sustainable mobility. So with all our projects that we have in our product portfolio, even if they are coming from aerodynamics, structural lightweight, precision components, propulsion, and battery solutions, they all contribute to a more sustainable mobility in future, by having the aim to lower overall vehicle emissions. Last but not least, for Röchling, we identify us as a full service tier 1 supplier. So we have the full services available to support the OEM, to support our customers in all related fields of development to our products. That is meant especially when you are coming to new technologies like metal to plastic bonding in this first 3 circles we have here on our value chain, especially starting from advanced development, from prototyping, going over to tool and equipment manufacturing to also be able to build in-house our manufacturing lines, and then have a dedicated material application center to develop with our suppliers, with our material suppliers, innovative technologies, innovative solutions for our components. Metal to plastic bonding. Why should I join metal and plastic together? First of all, looking at metal and the related applications in the ePowertrain field, we have good stiffness, we have good strength, we have good mechanical properties in all different regions of application, thermal or even more. And we have, when it comes to cooling, very good performance in this. So why should I use plastic then? We see with plastic very positive effects when we are coming to functional integration, especially when it comes to electrical isolation in the powertrain. This is something with metal we need additional treatments. And again, we have with plastic injection molding a lot of design freedom and cost-effective solutions. And we have a lot of different possibilities to adapt into the specific need material grades. So for this reason, by joining these 2 material types together, and you have seen this also in the previous slide about our portfolio, this is a trend we are seeing very often in different application fields, also for structural lightweight. The benefits are clear: cost reduction, weight reduction, and also a sustainability aspect. And so we are liking to join these materials together. We are using them in our production, our components, and there are different principles to join this material together. You cannot weld them, this is clear, they are too different. But on the other side, when it comes more to mechanical connection, we can use kind of fixation with fasteners, we can glue them together. Or what we are looking into, especially as a plastic manufacturing company, hot bonding, and there are 2 different main processes. Physical interlocking, create undercuts in the metal surface where the molten plastic can flow into and create a leak-tight adhesion, or which is reserved to some specific material grades, family of polyamides, chemical bonding, where we can use a very, very thin adhesion promoter on the metal to join in a leak-tight way. And this is then the clue of this whole product approach to create a leak-tight adhesion between the two materials. You might wonder, different thermal expansion coefficient. This is the main, I would say, driver and the main hot point to solve in the development of such a component. And we can say that we have a holistic approach to define this material joint even better. What are we doing? First of all, we have standardized, let's say, containers or samples to test different material grades with different joining principles to make a first hybrid joint characterization, to gain data about tensio-torsional stiffness, about burst, about aging, and to define a digital then failure criteria of the joint. Starting from this, we are going to our CAE modeling. We are trying to create there a standard approach to apply this material knowledge, this material joint knowledge on a component. Do then a physical component manufacturing. In this case, it is a more an emphasized hybrid degas bottle to test in a very, very clear way what is the hybrid joint performance. And this is then a closed circle, because the more we have, the more we are able to gain data on this, the more we can optimize our simulation model and scale it up to much bigger components. So as I said, we are starting with hybrid joint characterization, simulation, and are able then to produce different hybrid components with leak-tight adhesion. This is technology. But of course, we need to bring cars on the street, and anyhow, at every point, we need physical components. And we see, when it comes to electric mobility and ePowertrain application potentials for this technology, different ones. Starting from charging and conversion with onboard chargers, combined modules, low voltage, high voltage systems, battery management, battery cooling, e-motor components. We have also in our booth outside a first, I would say, cooling jacket, a hybrid cooling jacket manufactured, which is very, very, I would say, one of the major difficulties when it comes to join this material together, because you cannot pressurize them. And at the end, what is one of the newest application fields that we are currently looking into, power module cooling, using a plastic cooler and join this to the power module. So, solution study, high voltage DC-DC converter. We have taken here as a benchmark in our advanced development activities a DC-DC converter from a Volkswagen Group vehicle. We have done analysis. We understand that which are potential solutions to change from a pure aluminum die casting housing, which has a weight of 3.3 kilograms. So multiply this by the several high voltage power electronics devices in the car. We have a lot of aluminum that we are having, a lot of weight on the car. We have reverse engineered also the signals. We have tried to understand the major requirements. We have developed a concept, material sampling, testing, and brought this to a digital solution and to a B sample, which we there validated on two main functions. First of all, electromagnetic shielding, which is very important when you use plastic. It is not that efficient for certain regions of electromagnetic emission, and validated this also on a final, I would say, running system with cooling system working. How is the concept looking like? We have also then on the booth our physical demonstrator. We have here the cutted section, so we have the power electronics in the middle. We have used a hybrid cover also. And the biggest innovation is by realizing this main housing, where we are using a deep drum aluminum shield. We are using a PA66 main housing, the black one, and the white one is also a PA66 cooling channel cover. Why two different colors? We have also two different colors at our demonstrator there to showcase that we are using here two different material grades, one laser absorbing, one laser transparent one, to use laser welding for joining. And in the specific regions where we have openings of the plastic, to have a direct water glycol to aluminum contact, where we right there have the biggest necessity in cooled power electronics. Right there we need metal to plastic bonding. So we are bonding here these two materials together without any sealing ring, without any screw. It is a hot bonding process, so we need to heat up in this way the aluminum. The aluminum transfers the heat to the plastic, melts it, and then we have with the chemical adhesion promoter with pressure a leak-tight adhesion. So this is also fully integrationable in our production facility. And this is the very big innovation on this topic. As I said before, we have done two major tests at the moment. EMC testing, comparison between the die casting housing and our hybrid housing. Both are respecting the VW standard TL 81000 for emissions. And on the second step, we have tested also the hybrid joint, where we have, I would say, a joint which is stronger than the plastic welding. And this was then the main, I would say, confirmation that this will work. In parallel, what we are doing with the samples you have seen before, especially with the hybrid degas bottle, we are also doing different kinds of long-term validation, aging, pulsated pressure, thermal cycling. And we can give you, for example, an indication that the burst pressure on a simulation level compared with that what we are measuring then on the physical component has a variation, a gap, which is lower than 10%. And so we are quite confident in the next steps that we are bringing also this digital experience to simulate the components to a next level and to be pretty sure when it comes to developing, designing a component and making a validation on the digital twin, that this will then also working on the physical component. Let's talk about the benefits of this housing. We have run also a cost estimation. We can save here with our calculations compared to the state-of-the-art aluminum housing roughly 25% in costs and roughly 40% in weight, which is a great result. We are coming from 3.3 kilograms to 1.8 kilograms of overall weight. So discussing this with different OEM customers, you know, all of them are searching grams. Here we can really have a big impact then on the system weight. GWP reduction potentials, we see also potentials here in reducing the global warming footprint, the CO2 footprint of the system. Of course, it's clear we are joining here metal and plastic. We need also to think about sustainability, about recycling. It's a leak-tight adhesion, so you cannot simply remove it, but you are other processes, mechanical process to shredder it and then to separate it. A very important point is when it comes to design freedom and the characteristics to use plastic in such housings. Plastic is isolating, so we see also your potential to integrate directly into the housing, then connector heads, high voltage connectors, low voltage connectors, signal connectors. And this gives us a really positive outlook to future applications. With this, I'm coming also to my last slide, because then I would like, of course, to answer your questions and especially then invite you to our booth at the exhibition, where we can go in a deep dive also on this new application potential that we are developing together with Infineon. So to substitute the aluminum die casting cooler or sheet metal cooler with a plastic cooler, using there also hot bonding to bond the metal cooling plate to our plastic cooler and have so a big design freedom when it comes also to integrate the single small system into a bigger component also inside the future e-axles that will come to the market. The benefits of this are clear, like I've said before, lightweight and cost effective. We can reduce the BOM. We don't need any fastener, we don't need any sealing ring, and the design freedom, as I said, is very important when it comes to plastic injection molding, and this is then when we need to go in discussions with the producer of this of the system. With this, I would like to thank you for your attention, and For questions, I am here, or during the break then also an exhibition. Thank you.